Hi guys, Sujadu Sen again with a new video. In this video we are going to check the design of a square column for biaxial loading. This is the problem number 7.8. The conditions are as follows. Determine the required square tight column size and reinforcement for the factor load and moments given. Assume the reinforcement is equally distributed on all four faces. The ultimate load is 1200 kips. Ultimate moment in x direction is 300 kip feet. Ultimate moment in y direction is 125 kip feet. F dash C is 5000 and Fy is equals to 60,000 psi. Since these values are given in ultimate load, so nominal loads are calculated by simple formula that ultimate load is divided by a factor of phi. For column, factor of phi is 0.65. So 1200 is divided by 0.65. It comes out to be 1846 kips. Similarly, nominal moment in x direction is obtained by dividing the nominal moment as the ultimate moment in x direction divided by the factor phi. This comes out to be 461.5 kip feet. And nominal moment in y direction is 192.3 kip feet. When this problem is solved, it is assumed to take a 24-inch square column, and as per the calculation by PCA column program with the interaction diagram, the suitable bars selected are 4 number 11 bars. These 4 number 11 bars will give an area of reinforcement which is equivalent to 6.24 square inch, which is almost 1.083% of the concrete area or of the total area. Now let us go and check what STAAD can do. I have already modeled this column. Same 10 feet. Properties 24 inch by 24 inch. Loads are defined. I just defined only one load, that is the ultimate load. Here you can see the vertical direction Fy is equals to 1200. X moment is 300 and Z moment is 125 feet cube. Then came to designs. And the concrete design, Fy is defined as 5 KSI, and I have to design this column. So let us run and see what the result is there. Let's see the output. Concrete design, only one member. So this column is designed for axial and bending. Fy 60,000, F-C 5000 psi. It is a square column, 24 by 24 inch. It is tied one, and it says only minimum steel is required. Area of steel comes out to be 5.76, where they have calculated a little bit higher, which is 6.24. So it's near about 1%. It's slightly more. It's there. They distributed 20 bars, number 5, 20 bars, and the area comes out to be 1.076%, which is slightly less. That means this is perfectly okay. And then STAAD also gives this interaction diagram. To understand this interaction diagram, this P naught is 2793, Pn max is 2234, P balance is 1076.93, M balance is 811.91, M naught is 329.34, P intention is minus 372. For design 1846. In Z direction, design moment is 192.31. Same thing is repeated for Y. The only difference is the moment in Y direction is 461.54. If you remember, in our example, Pn was calculated as 1846. For the design, Pn is 1846 and design moment was 192.31 exactly, 1846 and 461.5, so it converts exactly the same thing. Now let's see what the interaction diagram says. So let's go back to the problem. Let's see the interaction diagram. Here is the interaction diagram. Here you can see that P naught or maximum P max here is something between 2500 and 3000. Whereas if you remember, STAAD calculated P naught as 2793.6. This is the P balance, which was 1076. This is 500, 1000, 1500, so a little bit more, that means okay. And balance moment is something around 800 something. In the STAAD it was 811.91, it is slightly higher. The tensile value of force was in STAAD, it was minus 372. It looks that this is okay. So that means STAAD has generated a very similar interaction diagram, which we can see is here. So what we can conclude, that STAAD can design columns correctly, a concrete column correctly. So hopefully it will make a clear understanding, and hopefully you will like this video. Don't forget to subscribe. Thank you very much.